Welcome to the Calculus BC video for skill number 231. I can use derivatives to solve problems of related rates. And featured below we have a sculpture made from the saddle of a bicycle and the handlebars of a bike. And the trivia question is, what is the type of handlebars that are being used to create this sculpture? Alright, we'll start our notes on page 231A, and the first thing I did was I outlined the problem-solving strategy for these related rate problems, and you can pause it and write this all down, but we should read carefully and understand the problem. It's important that we draw a diagram so that we can notate what different symbols or variables mean within. Then we're going to try to express the given information in rate of terms of derivatives. So express the given information and the required rate. Write an equation that relates the various quantities of the problem, and sometimes you can use substitution to limit the number of variables, but don't substitute in your known values too soon. That's the most common mistake people make on these. Step 6, differentiate both sides with respect to time. And step 7, you substitute your known values to solve for the unknown values. With these related rates problems, we commonly see some formulas pop up over and over again. We have the Pythagorean theorem that's usually going to show up, and then we also have volume and surface area equations, or even area and perimeter equations. We're not limited to these equations, but I've noticed that usually it falls into one of these three categories. So I've got two examples that I walk you through. One of them is a area problem, that's example 1, and the other one is a Pythagorean theorem problem, which is example 2. The example 2 is very similar to the AP style question that I saw for last year's test. So the AP test question. So take heed to try to understand that example the best, because it is more complex than the first one. Alright, so oil spilling from a ruptured tanker spreads in a circle on the surface of the ocean. Oil is leaking out at 12 pi meters squared per minute. And how fast is the radius of the spill increasing when the radius is 15 meters? So what we have is we've got, our ocean, and then there's a break in the pipe right here, and oil's floating to the surface at a rate of 12 meters squared per minute. And so now that I understand the problem, I'm going to draw a diagram and introduce some notation. So the key thing is we have our radius, and over time the size of the circle is growing. And then I go about defining my variables. I'll have r as my radius. At the point of interest, my radius is 15. I've put an asterisk with dr dt because that's what we're asking us. How fast is the radius of the spill increasing? So that's our goal. That's what we want to figure out. And we know something about area, and we also know that the change of the area is 12 pi. So when we're talking about circles, a common formula for circles is the area formula, A equals pi r squared. And when we take the derivative of that with respect to time, we need to apply the chain rule, and we get dA dt equals 2 pi r times dr dt. And at this point we can substitute our values in. So we've got our dA dt is 12 pi, so we plug that in, and then 2 pi r, our radius of interest, is 15, so we can take that radius of 15 and plug it in. And when we solve that all out, we find that we can find a dr dt of 0.4, and the units would be meters per minute, because radius is a measure in meters and our time is per minute. So at the point where the circle, the oil spill, has a radius of 15, the rate at which the radius is growing is 0.4 meters per minute.
So that is a pipeline that is busted and is flooded the neighborhood and is going all the way to the drain at the end of the street. Luckily, our house is here, which is seemingly unaffected, but the smell is unbelievable. I mean, look. Incredible. And that is oil.
In our second example, we're talking about a particle traveling at 8 meters per second north from point P, and 50 seconds later a second particle starts traveling 10 meters per second east from a point, and that point is located 300 meters east of P. So we've got the first particle is going north, and then when the second particle starts, it's going to be traveling east. And so for diagramming this, I created two different times. The first time was when the first particle left, and it left our point and at a rate of 8 meters per second. After 50 seconds had transpired, our particle had moved a total of 400 meters, and our second particle, which is at 300 meters east of our start point, starts moving. So what we've done is we've created a triangle, and we can use the Pythagorean theorem to find that the distance between those two particles at 50 seconds is 500 meters. And we're trying to find at what rate is their distance from each other changing. So we're looking for the change in distance with respect to time. So I've put an asterisk with that one. And all the other variables I assigned and gave values to. And the relationship between all these values is found in the Pythagorean theorem. So I created the Pythagorean theorem, x squared plus y squared equals distance squared. And then when I go about solving it through the related rates method, what I want to do is take the derivative of both sides with respect to time, and I get 2x dx dt plus 2y dy dt equals 2d dd dt. Some students might be inclined to, at this time, simplify and cancel the 2 from all three pieces, and that's fine, you can do that. It still works out to be the same. But we go through and we plug in each of our known pieces and solve for dd dt, and we find that the change in the distance of the two particles at 50 seconds is 12.4 meters per second. Alright, hopefully these two examples helped you understand what exactly it means to use derivatives to solve problems of related rates. There is many kinds of ways this problem can be asked, and this is one of the key types of problems the AP test goes to for the free response questions. And the answer to the trivia question is the handlebars that are being used in this sculpture, those are called drop handlebars.